Okay, 33. So keep in mind we're in the calculator part now here, so they may or may not need a calculator. But actually 33 is the graph that we need to kind of interpret here. And we got figure above shows the graph of the function that has horizontal asymptotes at y equals 3 and y equals negative 3. And it says which of the following statements are true. So this statement reads that the derivative is less than 0 for all x greater than 0. Okay, so once we get past 0 here, is the derivative negative? It's going to approach that asymptote. Okay. Keeps getting smaller and smaller. Does it ever actually get to the asymptote? No. Okay. Infinitely close to 0, but is it ever going to get to 0, the derivative? So what could be said then about number 1? So is that true? That the derivative is less than 0 for all x greater than or equal to 0? Yeah, that's true. Alright, how about the next one? Number 2 says the limit as x approaches infinity of the derivative is equal to 0. So as we approach infinity for this function, does the derivative approach 0? Yeah, it gets continuously decreasing here. It's going to decrease, but ultimately the slopes right here maybe is say 1 or something, negative 1 that is. But as we move to the right, the slopes are getting closer and closer to 0, aren't they? So therefore, what could be said about number 2? True. And then the other part here says, how about number 3, that the limit as x approaches negative infinity, the derivative approaches 3. Well, here's your approaching negative infinity. Is the derivative approaching 3 here? Why might somebody say yes to that? The function's approaching 3, but is the derivative approaching 3? What's the derivative approaching? 0. Okay, so 3 is out, so therefore it should be letter D, 1 and 2 only. Questions on anything on that one? So what's the general rule on that problem? Read carefully. Make sure you know whether we're dealing with the derivative or the function or what. Just make sure you look at the notation carefully. Here you go. What else? Josh?
36.
Alright, 36. We have, it says the derivative of a graph f of x, prime of x is given by e to the x and negative x cubed plus 3x minus 3. And we're dealing with 0 to 5 in terms of intervals here. It's a closed interval, keep in mind. And the question says at what value of x is f of x an absolute minimum? So we're looking for an absolute minimum here. And so ultimately, anytime we have an absolute minimum, we want to think about the candidate test here. Now keep in mind that we don't know the values here for 0 and 5, so if we want to try to find f of 0 and f of 5, which are the two endpoint values, okay, we don't have the actual function. We could try to anti-differentiate this, but as you can imagine, that's going to might be proved to be difficult. But more importantly, we also know that the minimum candidates are going to be when the derivative equals 0 or the derivative doesn't exist. Well, equaling 0 really is the only option here because this is never going to not exist. It's going to be an all real numbers domain here. So if we look at our picture of this thing, we got e to the x times negative x cubed plus 3x minus 3. If we go ahead and put that in, and we'll do we'll do our window 0 to 5. And our y window, I got negative 5 to 5. That might be okay, might not be. We'll find out. So we can see that, and looks like that's it. Huh? So let's interpret. So when we're at f, when f is at 0, the derivative is negative. Remember, we're looking at a picture of the derivative here. Keep that in mind. The derivative is negative, right? So if I were to kind of mirror a picture of my function itself, okay, wherever it may be, we don't have any function values here, but bottom line is, let's just say for argument's sake, it starts there. Okay, the derivative is negative for a little bit, right? Okay, so that means it's going to be going down from that point, from the left end point. Okay, and then once it gets to this point, the derivative is, this is the derivative is 0, right? and then the derivative becomes positive. Okay? And so if the derivative becomes positive for a while, and then what happens at this point? Derivative 0 again, and then it becomes negative. And if the derivative becomes negative, so ultimately it might have some kind of shape like that maybe. Just, again, this is a real rough picture, but bottom line is it does mirror the values. We got negative values here, positive values here, negative here, derivative negative, positive, negative. Okay. We got 2 points here where the derivative equals 0, changing from negative to positive, then positive to negative. Okay, would give us a minimum here and a maximum here. All right. Now, so the question then becomes this. Is where does the derivative, or at which value of x, okay, does it have an absolute minimum? Well, again, we know that this first one is a minimum, so that means that point right there would be a candidate. Okay? So if we find that point, we use our 0 command and find it. We get 0.617, and you notice that 618, that's letter C. Right? But here's the key though. What did they give us at the beginning? Or what kind of interval? So what kind of interval is that though, since it has these? It's closed interval. So that could be the minimum, but think about this. After we get to this maximum point, what happens after that? It's going to decrease for good, isn't it? Okay? And based on the slopes that we're getting here, I mean, slopes are getting really negative really fast, aren't they? So what should we expect then? Is this actually going to be the absolute minimum? Now, once we get past that maximum, we're already at the maximum at 2 something. We're going all the way to 5 here. Okay? Those derivatives are going to be very big, which means that our slope is going to carry us down way past that other minimum that we have here. So really, where is the minimum point then? It's going to be at 5 then, isn't it? Alright, so remember the end points are candidates, so you consider all the candidates, which are going to be all critical points, end points, stationary points, singular points. Questions on number 36? What next?
37.
And 37, we have a table given, and the question says, the table above gives the differentiable function of f, and it says what is the approximate value of the derivative at 4? Well, with the table that we have there, we essentially have an xy chart. True? So if we wanted to estimate the derivative there at 4, okay, then couldn't we just calculate a slope with these points? These points are very, very close to 4, aren't they? So if we use like this one and this one, the second and third, or the third and the fourth, or the second and the fourth, and maybe the second and fourth might be a good one, because that will give us 2 points that are on either side of 4. Okay. So if we calculate those, and we type in our y values, if we do the second and fourth, we'll say we have 1.16016 minus 1.15548. So there's the top, and if we divide that by 4.001 minus the other x value, 3.999, 2.34, which corresponds with letter D. What else? Mike?
I have a question about 35. What do you say is an inflection?
So we're given the picture here that says this is the graph that shows the distance from a reference point, particle moving on a number line. Which of the points marked as closest to the point where the acceleration first becomes negative? So remember, if this is essentially it's a position function. True? So if it's a position function, okay, the acceleration would be the second derivative. Okay? And so the second derivative here, we're looking at concavity. So what do we got going on here in this first part? This is concave up. Be concave up, and then it goes to concave down. So where does it change? It changes at C, doesn't it? And wouldn't C be where we have the change in concavity out of any of those choices? this being a position function, we're just looking for acceleration, which is the second derivative. So we want to know when does the second derivative change from positive to negative in this case. So again, concave up here, concave down here, changes at C. Next. Alright, 39 we have, so as we got an interval here on 0 to 5, we got cosine 2x, sine 3x. Says they intersect at 4 times on that interval. And the question says that A, B, C, D be the intersection points between 0 and 5. And we want to know which of the following definite integrals has the greatest value. So my suggestion would be to graph. So the two functions that we have here are cosine 2x, sine 3x. And if we make our window, it says from 0 to 5, so we already have that set up. Negative 5 to 5, since these are sine functions, cosine and cosine, both with an amplitude of 1, I'm going to change this to negative 2 to 2 so we can see it a little bit better. So remember, this is the cosine function. You'll keep track of which one's which here, keep in mind. So the cosine one is the one that starts at 1, 0, or 0, 1, which shouldn't be terribly surprising. All right, so the question is, which of the following integrals is going to be the one that has the biggest value? And notice that all the integrals are the subtraction of those two. So in other words, they're all the area between the curves. Okay? And so let's take a look at this one. If we look at this area, and this area, these first three parts, okay, no matter whether they have them arranged right or not, okay, are any of these three areas bigger than this one or this one? No. So what are we looking at here? We're looking at this one and this one. Really are only two candidates. Remember, the intersection points are 0, A, B, C, D, and 5. Right? So we got between C and D, and between D and 5. So out of our choices there, which one's the only one? Which ones are the only ones that are relevant? Yeah, D and E are the only reasonable choices, aren't they? And if you look at that, is there even one that even considers this area from D to 5? So really, it's just this one. So what's going to be the difference in terms of which one of those has the bigger value? Why would they have different values on those two? Why are D and E, why would they even have different values? What's different about D and E? Now, one has the subtraction the right way and one has it the wrong way, right? So basically, what's our job? Figure out which one's the right way. Okay? So let's look at the cosine function here. Remember, this is the cosine function. Okay? And the cosine function has an amplitude of, or it has a 2x, so it's going to have less cycles, if you will. So that's going to be here. It's going to be this one. This part is the cosine on top. So the cosine's on top. So if we want to have a positive value, our integrand better be cosine minus sine then, huh? Okay. Which one is cosine minus sine? That should be D. What else?
You're 45.
45, it says if y equals x, e to the x, and dny dxn is the nth derivative. And what we want to know then is, can we write an expression for the nth derivative of this given equation? And so to do that, we might, best bet here is probably try to look for a pattern. So let's see, what's the first derivative? If we do first derivative, what rule are we going to have to use? What's going on between x and e to the x? It's product. So we use product rule. So first times the derivative of the second plus the second times the derivative of the first. So that would ultimately be our first derivative right there. True? Second derivative? we have x e to the x. That's the same thing we just had last time, right? So the derivative of this, isn't it going to be this exact same thing if we do the product rule? So again, this part is the derivative of that, and then plus e to the x again, because the derivative of e to the x is e to the x. And if we do y triple prime, the derivative of that we know is what we got the first time, x e to the x plus e to the x. The derivative of that piece is e to the x. The derivative of that piece is e to the x. See a pattern developing here. So ultimately the nth derivative is going to be x e to the x. That's going to be part of it. And then it's going to be plus. How many e to the x's do we have here? Well, we have 1 here, first derivative. 2 here, second derivative. 3 here, third derivative. So how many are we going to have in the nth derivative? There'll be n of them, isn't there? And that corresponds to none of them, because what they do, and again, keep in mind, don't think that you're wrong just because it doesn't look exactly like what they have. And bottom line is they both have an e to the x in common, so if we did that, wouldn't that look like letter C? Factor e to the x out. What else? 31 to 45. Justin?
Yeah, that's
41. 41 says we have a function whose values are given. The 0 to 6 area of that function is approximated by a Riemann sum using the value of the midpoint with 3 subintervals of width 2. And we want to find the approximation. So we got values on there from 0 to 6. So if we're going to use a midpoint Riemann sum with 3 subintervals, that means we're going from 0 to 2, then 2 to 4, and then 4 to 6. So each length is going to be 2 of our rectangles that we're drawing. We have uniform subintervals. Okay? And then the heights are going to be measured at the midpoints. We want midpoint Riemann sum. So what's the midpoint of 0 and 2? That's 1. So what's the height at 1? 0.25. The midpoint between 2 and 4 is 3. So that would be 0.68. Oops, one more, sorry. So 0.68 there. And then the midpoint between 4 and 6 would be 5. It would be 0.95. So ultimately those would be the heights of the 3 rectangles that would be drawn. And if I take that and multiply it by 2, it would turn out to be D, 3.76. What else? 31 to 45. Victor? 42, we got, says d dx, the derivative of the integral from x to x cubed of sine of t squared dt. So ultimately it looks like a fundamental theorem problem, but we can't apply the fundamental theorem because we have a variable lower limit. Okay. So the way we remedied that is that we rewrote this argument of the derivative part here into the following. We wrote it from 0 to x cubed of sine of t squared dt minus 0 to x of sine of t squared dt. Because remember, if we take the whole area from 0 to x cubed and we subtract the area from 0 to x, we'd be left with the area between x and x cubed. Okay? So if we rewrite it like that, now we can take the derivative of that whole expression and apply the fundamental theorem. So the fundamental theorem tells us that if we have an area function, that the answer here is the derivative of this integral function is the integrand evaluated at the upper limit. So it would be sine of x to the third squared, so that would ultimately be x to the sixth, times the derivative of the upper limit, which is 3x squared in our case. And then in this one, it would be the integrand evaluated up the upper limit, so it would just be simply sine x squared. Because if we put our x into t squared, we get x squared. The derivative of the upper limit is 1. And so that right there would be our answer. So let's see if that matches up with any of our choices. Looks like it matches up exactly with letter C. So again, key issue is that to find the derivative of an integral function, we can use the first part of the fundamental theorem. But the problem is if there's a variable lower limit, then we have to change that argument first into that subtraction situation. So 0 to the upper limit minus 0 to the lower limit. That is the same thing as the area of this. Now, one question is, why did I use 0 here? Would it have mattered? I mean, ultimately, did the fundamental theorem, does it depend on what this value is? As long as it's constant, as long as it's some a, then it doesn't matter. I picked 0 just because it's a cool number. What else? Go ahead. 43, we have a rate function given. This is a tank filled with water at a rate of 300 radical T gallons per hour. So this is our rate function. It's measured in gallons per hour. Time is greater than 0. If the tank is originally empty, how many gallons of water are in the tank after 4 hours? So this is a pretty typical problem that we just got done doing with our rate function. If we know our rate function is this, if we were to draw a picture of it, it'd be gallons per hours versus hours. So what would the area underneath it give? Gallons per hour times hours, which would give us total gallons. So isn't it just simply the integral of this function? And it says after 4 hours, so it'd be times 0 to time 4. And since it's on the calculator part, how much time should we spend finding an antiderivative for that? None. Okay. So do your math 9, 300 radical x. And we get 1600, which is letter D. And keep in mind that also relied on the fact that there was no water in the tank at the beginning. Remember, had they given us some water in the tank at the beginning, we would have taken our 1600, which is the accumulation, and added it to something. In this case, the something was 0, so straight up 1600. What else? 31 to 45. 34, we have a volume problem. It says that the region in the first quadrant, bounded by the graphs of y equals f of x, and y equals 2 sine x, which is ultimately something like that. And you could graph this with a calculator if you can't visualize that. It's revolved around the x-axis, and if we revolve it around the x-axis and we keep it into a vertical slice, okay, what shape would be created then? Be a washer. So our washer setup is going to be pi times something squared minus something squared dx. The integral here, limit-wise, is going to go from 0, we can see, to whatever that intersection point is right there. And that intersection point, if you graph it, 2 sine x and x, and use our intersection command. May or may not be a nice answer. In this case, it's not a nice answer, but that's why it's in the calculator part. 1.895493. 4943, that is. So that would be our upper limit. The outside radius of the washer is going to be defined by the sine function. So we'd have 2 sine x in here would give us the outside radius of the washer. The inside radius would be the other function, the bottom function, which would be the x. And so ultimately that would be our integral. And again, it's a calculator problem, so use your math 9. And our integrand here would be 2 sine x all squared minus x squared on 0 to 1.8954943. And that is our result. However, remember that is going to be that times what? So we'll get that 2.1255, etc. So we still have a pi out in front, so we can multiply that by pi. We get the final answer, which is 6.678, which looks like letter D. when the washer set up. All right. Anything else? 31 to 45.